Hello, YouTube. Welcome back to another episode of 70 Years of Moving Mud, a history of iron bombing. This is episode 28, Precisely. And as I hinted last time, today we're kind of going to begin a new chapter. Up until now, the title and the stated intent of the podcast, we've been focused on the iron part of iron bombing. We've been talking about the aircraft themselves and the men who flew them. But in researching the period of the middle 1960s, as we move past the early Vietnam War period, I started to realize that there really was a shift away from true iron bombing, and I think for, a very good reason. And I think different people arrived at the same basic conclusion from many different directions. The fundamental truth that just about everybody involved in combat operations in Vietnam was starting to confront, if they were paying attention, was that the whole approach to using an aircraft to drop bombs directly on a target from relatively close range, let's call it fighter bombing, as pilots and planners understood it in the Second World War in Korea when it was basically invented, it just wasn't good enough anymore the way it had been done until now. The facts on the ground were that with the technologies, techniques, and procedures that were available in 1965, U.S. air power was simply not delivering the effects on the ground that were worth what they were costing, in terms of casualties, but also in terms of really any other measure of military effect. Sorties, ordnance, logistical support, all of it was just a lot of effort spent to accomplish really too little. So immense effort was being applied for very little practical effect in terms of achieving the mission. Well, why? Well, like I said, I think there's a number of factors, but really, I'm going to say it boils down to something I want to call a practical precision. And by that, I mean that in the environment in which the pilots operated, under the rules and conditions they were forced to respect, they simply could not get enough bombs close enough to their targets to generate the effects they were expecting to achieve. Now, basically until the Vietnam era, precision in bombing was about the skill of the crew. It was about steady hands on the stick and memorized flight profile and nerves of steel in the attack room. Bombing accuracy was largely a human affair, aided by some basic tools, but still the key variable was the man in the seat. But Vietnam showed that this model was, if not broken, it was certainly right at the edge of where it could be applied. Not just because SAMs and AAA made it hard to stay steady on a bombing run, although they did, but because the modern battlefield had kind of changed to the point where it was really exceeding human beings' capacity to meet the challenge. As we've covered in an earlier episode, the U.S. doctrine of the 1950s still assumed that precision could be achieved by flying close and often flying low. The attack profile was come in under the radar, pop up at the last minute, deliver ordnance directly to the target. This was the idea behind aircraft like the F-105, fast, low-flying iron bombers built to punch through the defenses. But that doctrine had never really been practiced in modern high-performance jets, and basically, the faster and heavier aircraft got, the harder it was for them to get lined up on the target. You simply had to do it from farther away, and the harder it was to press the pickle at the right time, because the target was just moving through your sight picture too fast. And then the North Vietnamese, with Soviet help, changed even that calculus because dense AAA coverage, radar-guided SAMs, and better search radars made those low-level approaches suicidal. To even fly below radar coverage now meant getting below 500 feet, down to a level where the pilot was fully occupied, avoiding terrain, and had no attention left to spend on navigating or identifying the target. So, approaches were being conducted at higher altitudes, but then the modern integrated air defense system was making it necessary for pilots to attack targets from much greater distances and with much less time spent identifying the target and finding the right aiming point, because the amount of time that a pilot could afford to be exposed to the threat was getting shorter and shorter, and the need to monitor the threat and apply countermeasures was taking up more and more of the pilot's precious situational awareness. So effectively, what was happening during Rolling Thunder was that pilots were being forced to sacrifice precision for survivability. It was simply beyond human capabilities to deliver ordnance as accurately as it needed to be, given the constraints under which it had to be delivered. Now, there were two ways out of this predicament, I think. One involved changing the way the aircraft delivered the bombs, and the other involved changing the bombs themselves. So we're going to talk about those in future episodes. We're going to start by talking about the aircraft. Now, I mentioned low-level ingress a minute ago. I do want to take a minute back up and explain what I meant there just quickly. In the 1950s, low-level actually meant, a few thousand feet, maybe as much as 2,000 feet. And honestly, if you want proof of that, notice that the A4 and DCS, which is one of the earliest implementation of terrain clearance radar, in that aircraft, the terrain clearance threshold is set to 1,500 feet. That's low as far as the A4 is concerned, and that number can't be changed. So the point was, though, that 1,500 to 2,000 feet was enough to stay below radar, at least for as long as you needed to in many cases. But also more to the point, if you've ever tried flying in a flight simulator, you know that 1,500 or 2,000 feet is high enough to give a pilot enough situational awareness to find a target and line up on it properly for a dive bombing or even a shallow angle attack, especially if you're only flying at a couple hundred miles an hour. But by the 1960s, the threat picture had changed. The rise of radar-guided SAMs was in part due to improvements in radar, and then it spawned its own improvements in radar. And these improvements included increased resolution at longer distances, and they also included miniaturization of many of the components, such as the emitter and the detector, which meant that they could be raised on tall masts, which extended their radar horizon, which in turn meant that the height at which an aircraft would have to fly in order to avoid detection long enough to be a surprise to the point defenses, well, that altitude got lower and lower and lower, and suddenly low level meant 500 feet or 300 feet or 200 feet at 500 knots. And remember, this wasn't a one-time stunt. This was sustained terrain following flight, sometimes at night, often in marginal weather, in an aircraft that might be carrying 4 tons of ordnance and navigating by stopwatch and compass heading and manual map reading, maybe for hours at a time. And then you had to arrive at the target close enough to your initial point to be able to very quickly identify the target, get lined up on it for an accurate drop at Mach 0.8. The psychological load was intense, and pilots described it as flying inside a tunnel or surfing the earth. There were no second chances. A small miscalculation, a ridgeline missed by a few seconds, could be fatal, but more to the point, even a small miscalculation would put you in the wrong place at the wrong time with no hope of getting close to the target. It really was at the very outer limits of human capabilities. I mean, even with very extensive training, only the very best pilots really were truly proficient at it. In effect, it meant that to perform this task proficiently, even good pilots needed help. First of all, they probably needed another body and brain and set of eyes in the cockpit, which is why there's a sudden profusion of 2-seater aircraft that appear in the 60s. But beyond that, it just wasn't enough to be a good stick anymore. You needed the airplane to be able to help you, to stay alive, so you could worry about being effective at all of the executive functions that you needed to get your ordnance where it needed to be. You needed systems that could tell you what was ahead of you with enough warning to avoid having to make sudden changes. In other words, you needed a terrain clearance radar. You also needed a system that could give you cues to tell you how to fly to arrive where you needed to be, when you needed to be there, so that you could focus on finding and engaging the target when you arrived. In other words, you needed a precise inertial navigation system. Now, eventually these systems would also be integrated with a full autopilot that could accurately fly the aircraft based on inputs from the radar and the INS, thus freeing the pilot's bandwidth to really operate the platform. But that was still a little way off. In the 1960s, at the time, the pilot still had to fly the jet, but increasingly he needed to have a computer giving him good, accurate guidance on where he needed to fly and what, if anything, was in the way. The reward was real. With a true low-level, high-speed, precisely navigated approach, it was possible for strike aircraft still to surprise the defenses, and in the short window that surprise has afforded them to identify the target and accurately deploy their weapons without being engaged, distracted, or destroyed by enemy air defenses, which, as Rolling Thunder demonstrated, was simply not possible with the old technology by 1967. Now, the other tools that pilots really needed to get in as aircraft got faster and exposure time got shorter was just plain old help knowing how to release their bombs and when. I mean, it was quite clear in the era of World War II that it was very possible for dive bombing attacks to put bombs very close to targets, even when the target was moving, like a tank or an aircraft carrier. But these attacks were conducted in near vertical dives at speeds around 200 miles an hour, and often starting at 10,000 feet. Now, again, if you've tried this in a simulator, you know that this attack profile is disconcerting. And it takes a great deal of practice to get comfortable with it. But once you do, it is actually a very accurate method of hitting the target because the sight picture develops relatively slowly, and there's plenty of time to choose your release point accurately. Conversely, if you've ever tried a high-speed, shallow-angle pass in a high-speed jet, you'll know that while it's a lot more comfortable and easy to set up, it's much harder to perform accurately and much harder to hit the target reliably because things just happen too fast. There's very little time to correct, and accuracy is highly dependent on choosing the right split second in which to press the pickle button. And of course, all of this gets harder the farther and farther from the target you want to be when you release. Now, we know how modern jets solve these problems. They solve them using digital computer technology that we all grew up with and considered to be quite normal and natural. But almost none of that gee-wizardry existed in the early 1960s, when the generation of aircraft that would fly in the latter half of the Vietnam War were being conceived and designed. But it was coming, and I think that the revolution actually in the end is what drove the major innovation in aircraft design from the 1960s, in about the mid-1960s into the mid-70s for sure. So before continuing, let's take a little side trip into the world of the semiconductor, because it really is the thing that's driving aircraft design from here on for a decade or so. You see, up until the 1950s, just about every piece of electronic equipment relied on vacuum tubes. I mean, to understand why, you have to go back to a little bit of physics and a whole lot of 20th century engineering. A vacuum tube is basically an airtight glass enclosure with metal electrodes inside. And this part's critical. It's under vacuum. The vacuum isn't just for show. It removes air molecules so electrons can move freely from one electrode to another without getting scattered. This is a principle that's known as thermionic emission, and it's basically the same thing that makes a light bulb glow. If you heat a metal surface, usually with a filament, it gives off electrons. This was first observed in the late 19th century by Thomas Edison and later formalized by scientists like Ambrose Fleming and Lee DeForest. In the most basic vacuum tube, which was a diode, you had two electrodes, a heated cathode, which was the electron source, and a positively charged anode. Electrons will flow from the cathode to the anode, but they won't flow in the other direction. This made the diode ideal for rectifying AC current because it turned an alternating current into a direct current. But then came the triode, with a third electrode. And this electrode was called a grid, and it was added in between the cathode and the anode. And by a bunch of gee-wizardry that I won't go into, it was found that by applying a small voltage to the grid, you could control a much larger current flowing from the cathode to the anode. And that's where the magic happened, because it meant that the triode could be used to amplify a signal, because a tiny modulation in the voltage to the grid could result in a much larger modulation on a much larger current between the cathode and the anode. And suddenly, audio signals, radio waves, and radar pulses could be made louder and stronger and more useful. This made vacuum tubes the heart of all electronics from about the 1910s to the 1950s. They powered early radios, radar sets, and both of which were core to military avionics during World War II and the very earliest part of the Cold War. In fact, the B-29 had more than 100 vacuum tubes on board, and the earliest air-to-air radar systems had even more. But there were problems. Because vacuum tubes were A, fragile, glass breaks, they were bulky. Imagine hundreds of not even so tiny light bulbs. They were power hungry because they needed to be heated constantly, and they were heat sensitive, and they often failed under vibration and thermal load. Worst of all, for aircraft designers, they were heavy, and they required lots of support circuitry that failed often, and it was also heavy. But for 40 years, they were the only game in town. Until the advent of semiconductors, vacuum tubes were the only way to build amplifiers, oscillators, and switches, the building blocks of pretty much anything electronic. Now, that changed, or started to change, in 1947 at Bell Labs when a team led by William Shockley, John Bardeen, and Walter Brattain demonstrated something completely new. They called it a transistor. Their experiment showed that it was possible to amplify and switch electrical signals using solid materials. No filaments, no glass tubes, and no warm-up times. Instead, they used a little bit of a strange property of silicon. Silicon is normally an insulator, meaning it does not allow electrical current to flow through it easily. But if you injected it with just the right amount of impurities into the pure silicon, you could, under just the right conditions, turn it into a conductor. And here the right conditions meant applying a small voltage across the junction between two different types of doped silicon. In other words, Shockley and company showed that you could replicate the vacuum tube diode and triode if you made the right sandwich of silicon layers. You could amplify a signal between the outer layers using a very small input voltage to the middle layer. Now, this may sound a bit abstract, but it was revolutionary. Shockley called the new device a transistor, as I said. Basically, it could do everything that a vacuum triode could do at a fraction of the size, weight, and power, and with no moving parts. In fact, the transistor could be made so small and so cheap that we literally carry billions of them around in our pockets every day. And this sudden, dramatic miniaturization of electronics meant that aircraft designers suddenly had the prospect of building much more sophisticated electronic systems that were also small, light, and rugged enough to survive the heat and vibration and g-forces of modern flight. Vacuum tubes couldn't do that, but transistors and later integrated circuits could. Thus, the invention and the rapid development of solid-state semiconductor electronics suddenly allowed engineers to build powerful and capable radar systems that, could fit into the nose of a fighter, or to design sensitive inertial navigation systems that could be hooked up to digital computers to provide accurate, real-time, continuous navigation data to pilots who were busy doing other things like avoiding ground and ground fire. Basically, it meant that it became possible to design the first truly coherent, integrated avionics systems where information could be gathered, processed, and displayed in real time, and which gradually became the thing around which airframes were designed, actually. But that was a little ways in the future. In the late 1960s, the revolution, though, was well underway. Well, the very first true air data computer wouldn't appear until the 1970s, let's say, with the F-14. But by 1965, the tech wizards had already invented some pretty serious pieces of technology that changed the game entirely from being able to sense the world outside the aircraft and synthesize that information into a picture that the pilot could process and understand, even in the heat of battle. In short, the transistor made modern avionics possible, and avionics made precision flying and precision bombing possible again. For the U.S., this was, in a sense, a godsend, because through the 1940s and even into the 50s, the main advantage the U.S. had over its adversaries, at least in terms of conventional weapons, really was quantitative rather than qualitative. In a very real sense, the Allies won the Second World War on the back of American industrial output. True, they sealed the deal with the ultimate technological leap, the atomic bomb, but even prior to Hiroshima and Nagasaki, the outcome of the war wasn't really in doubt, and it was American productivity and logistics that were the foundation on which that victory was built. And again, in Korea, the U.S.'s primary advantage was its ability to produce, sophisticated machines, but in much greater quantities than the North Koreans, Chinese, and Russians combined. True, there was a bit of a quality factor that had started to appear, but it was more that the U.S. equipment could be produced on highly precise machinery reliably, so that its designs were advanced over those available to less countries with less advanced manufacturing. But by the 1960s, even that advantage, like the U.S. nuclear advantage, had largely evaporated. The Soviet economy, in particular, was, in the early 1960s, demonstrating that when it really wanted to, it could keep pace or even outproduce the U.S. and its European allies. And that's where the U.S. advantage in solid-state electronics started to matter. In the 1950s, the transistor had been a laboratory novelty, but by the mid-60s, the U.S. was starting to build it into aircraft systems, and what that enabled was a whole new approach to delivering bombs. It meant more compact and reliable radar systems, meant early head-up displays that we haven't even talked about that gave pilots that real-time information without searching for it in the cockpit. It meant INS systems, borrowed from the space and missile world, which were enabling precision even in low visibility. And it meant radar altimeters and radar bombing computers that could calculate release points dynamically, even during evasive maneuvers. In short, avionics were capable of turning iron bombers into information processors, and flying the aircraft could become less about physical skill and more about managing all of the information inputs. And it was the U.S. semiconductor industry that gave them the real possibility of implementing this shift. Other countries simply did not have access to the same technology and weren't able to replicate that for quite some time, actually. So this is where the U.S. reliance on quality over quantity really started to play a role because although the U.S. systems were becoming more and more expensive, they were becoming much, much more effective, and there was a multiplier effect that was largely due to the advanced electronics that was being built into the systems rather than in the systems themselves. So in the next episode of the Iron Bombing Podcast, we're going to start talking about probably the earliest instances of those truly modern aircraft, not because of the aircraft themselves, but because of the electronics they hosted. We're going to talk about the A6, which was really at the very early edge of that. It was kind of a hybrid. And we're going to talk about the F-111, and we're also going to talk about the A-7, all of which served in Vietnam, and all of which brought a new approach that largely helped the U.S. restore at least some of its effectiveness in Operation Linebacker, although there was still a ways to go, and that's the story we'll take up after we finish with Vietnam. So that's going to be it for this week. Tune in next week when we'll talk about how precision was designed precisely into a new generation of aircraft. Thanks for listening, and we'll talk to you again soon.